Okay, thank you very much. Thank you to the organizers for inviting me, allowing me to give a talk here at this conference honoring Istrisky and Fejestot and Mackay. Thank you very much. I'm going to talk about a generalization of the planar Pq theorem, and I realized when I read over my abstract again, I didn't say what the Pq theorem is, so I apologize if you don't know that. I don't expect you to, and I will tell you what it is. And this is based on work with some of my students. I will mention their names later on. But this is related to Heli-type theorems, and Deborah already gave us an excellent introduction. So I'm first going to give you an overview of the basic Heli theorems that I'm going to consider. So Heli's theorem, I have a finite family of at least d plus 1 convex sets. Any d plus 1 members intersect, then there's a point that intersects every member. And what I'm interested in are the combinatorial aspects of Heli's theorem. Meaning, can I change the assumption that any d plus 1 intersect? And when I do that, then I must also allow for something other than a point. So I must change the conclusion. So something other than a point intersecting every member. Yes, a point or every member. And so these are what I think of as the combinatorial aspects. Deborah's talk was fixing the sets in the family to be more specific, right? Here I'm mainly interested now in changing these combinatorial conditions in the theorem. And I will also be changing the sets later on. Okay, so the first maybe combinatorial generalization of this we saw also last time. This is called the fractional Heli theorem, and the way you should think of it is saying that if many of the d plus 1 member subfamilies intersect, then there's a point that intersects many members. All right? And this you can quantify. This was done by Kachalski and Liu, who showed that there is some function. Some function for every d, there's a function goes from 0, 1 to 0, 1, such that for any family of n convex sets, if an alpha fraction of the d plus 1 tuples intersect, then there's a point intersecting a beta fraction of the members of F. Right? And this has turned out to be a very fundamental theorem in the theory of Heli theorems and intersection patterns of convex sets. And it was Kachalski and Perles, they conjectured actually precise bounds for this function. And I think this was based on some examples they found, some extreme examples they found, and they conjectured that this really is the extreme case. And their conjecture was proved by Kalai and Eckhoff independently. And this is a part of their theorem. Their theorem says even more than this. But the theorem says that if you have n convex sets and no d plus 1 plus r members intersect, then there's at most this many intersecting d plus 1 tuples. Right? And their theorem is called the upper bound theorem for convex sets because, in fact, they don't only talk about the maximum number of d plus 1 tuples, but they tell you exactly the maximum number of d plus 2 tuples that intersect, the maximum number of d plus 3 tuples. So in fact, there's something called an F vector, and they determine the maximum upper bounds of this F vector. And if you do a calculation, you see that you get this function 1 minus alpha to the 1 over d plus 1. That's this function in Kachalski and Liu that they had conjectured. And another reason for calling this the upper bound theorem, and Eckhoff notes this in his paper, is that the proof is very similar to the upper bound theorem for convex polytopes, for the face numbers of a convex polytope. And he says there that maybe there is some formal correspondence between these two. And later this has actually been shown, I believe, that there is a formal correspondence between this upper bound theorem for convex sets and the upper bound theorem for convex polytopes. So this is maybe the first combinatorial generalization, and it's very influential. The next combinatorial generalization is a colorful version. And it was Barney who described this. I believe maybe this form was first discovered by Lobas, and Barney discovered this in a dual form called the colorful Caroteodori, which Arnaud talked about on the first day. And it says the following: you have d plus 1 families of convex sets now. And then you suppose every d plus 1 tuple where you've chosen a member from each of the from distinct families, if all of these d plus 1 tuples intersect, then there is a point intersecting every member of one of the families. You don't know which one it's going to be, but one of the families, all the members intersect. You get Heli's theorem by setting the families equal to each other, so multiplied versions. And the dual version, this is the colorful Caroteroid theorem that we heard about before. And this has also been very influential, and many tools in discrete geometry have been developed from this single theorem. So very, I think, beautiful and important theorem. Okay, and then finally, I come to the Pq theorem. So this is maybe one of the major achievements in this area. So it was conjectured by Hadwiger and de Brunner, the following generalization of Heli's theorem, that for any integers p greater or equal to q greater or equal to d plus 1, you can compute some constant c such that the following holds, that if among any p members there are q that intersect, then there is a piercing set of size c. All right? There are c points, which and every member will intersect at least one of these points. And this was a major achievement when they proved this, and it used at the time this all state-of-the-art that existed for these discrete geometry problems and Heli theorems. It used the fractional Heli theorem, it used the colorful Caroteroid, and the things developed from this, like weak epsilon nets for convex sets. And it's a very beautiful theorem, and actually I think determining these numbers still, we don't know very much the precise bounds of these, and it's an important open problem in discrete geometry to know better how these numbers, this constant behaves with respect to p, q, and d. Okay, so that's the basic setup for the combinatorial versions of Heli-type theorems that I'm considering. I might have left out a few, but I don't have time to mention everything. One thing that is used in all of these theorems is the concept of optimization, sweeping some linear function. This is in the bottom of all of these theorems. This is an important thing that is being used all the time. Right? That lies at the foundation of all of these results. Okay, so now you've seen many of these combinatorial. You've seen all the combinatorial variations of Heli's theorem that I want to consider. So what can we do next? Well, one thing has been in common to all of the theorems. Although I changed many things, one thing was common to all of them. The sets were always convex. Now I want to consider something more general than that. Okay, so that actually goes back to Heli himself. In 1930, he discovered that you don't really need the sets to be convex. All right? What he showed that it's enough to assume that the members of F are topologically nice, and that the families are intersectional. Now let me say what I mean by this. Topologically nice means contractible, or if you like homology, you would maybe call it acyclic. It doesn't really matter. You choose one of these. Also, let's assume that the sets are open. That's what I'll do for now. But what it means, topologically nice, is just that the sets have the topology of a convex set, right? Which is very simple. And intersectional means that whenever you take members of your family, if their intersection is non-empty, then this intersection should be topologically the same as the members of the family. Right? So it's a closeness property. Right? So you define a family of sets, they have a certain topology, and when you intersect members, you stay within that set of that topology. Right? And as soon as your family satisfies these, then Heli's theorem holds exactly the same. Right? And that's called the topological Heli theorem. And of course, if you put in convex sets here, convex sets are nice. Of course, they have the topology of convex sets. And when you intersect convex sets, you get a convex set. Right? Okay, so I was going to say this. So the colorful and the fractional version, that was 1980s. A decade later, 1990s, you got the Pq theorem. And then about a decade later, various people were able to extend all of the previous theorems to the topological version. All right? So with the exact same assumption here, all the theorems that I told you go through. Right? But it took much more tools to make this work. right? So you have a topological fractional Heli. This one I write around 2000 because I don't, as far as I know, there's no explicitly written proof of this. But it has been developed. One has seen enough connections to things that one understands that this is true. And then you have the topological Pq Theorem, Alon, Kalai, Meshlam, Matushek, 2002. And then the topological colorful Heli theorem was the last one in this series. And the thing that makes these much more difficult theorems, maybe, is you cannot do this optimization technique, right? This is lost as soon as you switch to the topological setting, right? And that is where part of the problem lies. And I'll get back to later what are the tools essentially used here. But now I'm going to jump to the next decade. So that's our current decade. And so here I'm assuming that the sets are topologically nice. So natural question, what if the sets are less nice? Okay, not so nice as in the topological Heli theorem. And here is an example. This is kind of a folklore theorem, that a Heli theorem for connected sets in the plane. So you have a finite family which is intersectional of open connected sets in the plane. And I claim that the Heli number is 4. If every 4 intersect, then the whole family intersects. Okay? This is kind of a folklore theorem. I'll show you a nice proof of this. So the sets kind of look like the guy over here. And you can generalize this to higher dimensions, and you need some higher connectedness to do this. So for example, in R3, you would need your sets to be simply connected, not just connected. Okay, now this theorem was generalized further by Matushek. Well, he was very early, but then last year, a group, Go, Patak, Patokov, and Tanzer, and Wagner, made a very far-reaching generalization of this theorem, right? And when something's written in very small letters here, it means that it's a minor comment. You don't need to worry too much about it. Basically, what they did was to show that, in fact, you can have several connected components, and there can be many holes that you generally don't like in this kind of theorem, but you need to bound how many of them there are. There should be a constant number of them. Okay? Then they can prove a Heli number, but the number 4 becomes much bigger. And the reason is, well, this kind of Heli theorem is based on non-embeddability theorems, and if you want to have some slack, you want to allow your sets to be even more complicated, then you need to invoke Ramsey's theorem at some point. And in fact, they do Ramsey theorem and maybe a tower of height of a Ramsey number, and it becomes enormous. So these numbers are not practical at all, these Heli numbers you get. But their theorem, which I won't state here because it's too complicated, if you ever were in need to know that there is a bounded Heli number, this is a very powerful theorem. It's very general, and you can in many cases prove that there is a bounded Heli number. But it's going to be extremely large. If you actually need some good estimate of the Heli number, this theorem no longer works. Okay, so this is sort of where we are now, that we want to have sets that are more complicated than those in the topological Heli theorem. Okay, so let me show you the proof of this one. This is very nice and simple. So I'm going to prove it to you for families of size 5. So I have 5 connected sets in the plane. It's an intersectional family, and every 4 intersect. And I'll show that they all intersect, and then you can proceed by induction. Okay, so what I do is I take my 5 sets, and for every 4 of them, there's an intersection, and these black points are points in the intersection, and I've indexed which sets they're in. So this is in 1, 2, 3, 5. Here's 1, 2, 3, 4, etc. Okay, now for any 2 of these points, there will be 3 sets that contain this point, and the same 3 sets contain this point. Right? So here, 1, 2, 3, 4. Here, 1, 2, 4 is in this point, and the sets 1, 2, 4 contain this point and this point. And by the connectedness assumption, it means that there's a path from this point to this point contained within the sets 1, 2, and 4. And similarly here, there's a path contained inside sets 1, 3, and 5 that connect these 2. And now you connect every pair. And since there are 5 points, you're drawing the graph K5, which is not planar, so there's some intersection. Right? A pair of independent edges that intersect, and this edge is in 2, 4, and 5. This edge is in 1, 3, and 5. So the intersection point is contained in every member. And that's the proof. And then you continue. Now you know every 5 intersect, right? So then you can do it for every 6. Right? Sorry. Yes, now every 5 intersects. So now you look at a 6 tuple, and every 5 intersect, then you continue. And that's how you get the Heli theorem for connected sets in the plane. So this is based on non-embeddability, and in higher dimensions you have similar non-embeddability theorems, and you can prove something similar. But what the Guoquet and company sort of pointed out, and I talked to Xavier about this, is that this proof does not seem possible to modify to get these other more combinatorial versions, fractional, colorful, and Pq versions of this theorem. At least not as far as I know, and not as far as they know. So they wondered, can we get that? And that's what I want to present, that indeed this same theorem here, so that's what I will present, is that for connected sets in the plane that are intersectional, you get all the colorful, fractional, and Pq theorems for this kind of families. And I suspect that you would get it in any dimension with the right connectedness assumption. Okay, so that's what I want to present, but so far we can do it in the plane, and that's what I will show you. And it's based on, so now I need to switch setting a little bit. So we need to use something called the Nerves Theorem. Let me first tell you what the nerve is. So you take a family of sets, non-empty sets, and if you want to understand how these interact, how they intersect, the intersection patterns, you form this abstract simplicial complex called the nerve. And so the vertices of the nerve of the family F, the vertices are indexed by the sets of the family, and the faces of the nerve, the faces of this complex, are the subfamilies whose intersection is non-empty, right? And this is a simplicial complex. And you can do this for any set family, any set system. You can make the nerve any simplicial complex. There is a set system whose nerve is this abstract simplicial complex. Right? So this construction in itself doesn't really tell you very much. It's just encoding the intersection patterns. But that's where but when we deal with sets in some space, in a topological space, then we have a nerve theorem, something called a Nerves Theorem. And so for this purpose, let's suppose that the sets are open subsets in Rd. And then a nerve theorem says essentially this, that if the intersections are topologically nice for every face in the nerve, that's just saying that suppose the family is an intersectional family of topologically nice sets, then the topology of the nerve is essentially the same as the topology of the union of the sets. Right? So this is what a nerve theorem says. And I've drawn a picture here. Here are 4 topologically nice sets. It's an intersectional family. Here's the nerve, and this is homotopy equivalent to a circle, and this guy is homotopy equivalent to a circle. So the strongest form, when the things are topologically nice and it's an intersectional family, a nerve theorem, Borsuk's nerve theorem says that these 2 spaces are homotopy equivalent. Right? But there are other versions. That's why I just say a nerve theorem, because there are many, many versions of nerve theorems. Okay. Now, how does this relate to what we were doing? Well, of course, if I now look at my family of sets, it could be convex sets. If I look at the nerve, I'm encoding the intersection pattern. So all the Heli properties I can see in the nerve. If every d plus 1 intersects, it means that the d skeleton is complete. If an alpha fraction intersects, it means that the d skeleton is alpha dense. Right? If they all intersect, the nerve is this big simplex. So everything that you want to know about the Heli theorems is encoded inside the nerve. Okay. So one more definition. So a simplicial complex is called D-Leray if the homology vanishes in every dimension from D and greater for every induced subcomplex. Right? I'm using reduced homology. Yeah. And homology, I'm using rational coefficients, or maybe coefficients in a finite field. Okay? So this is a definition. We call this a D-Leray complex, any complex that satisfies this. I believe this is a name Kalai invented. I don't know. But, well, there's something called Leray's nerve theorem, which is one that he uses, yeah, which gives you the following. So a consequence of Leroy's nerve theorem is this one. If you have an intersectional family of topologically nice subsets of RD, then the nerve is D-Leray. Right? And this is the key point here. And this is, in some sense, a very weak non-embeddability theorem, if you want to think about that. If you want to think of it in this way. The non-embeddability theorems that they use to prove that previous Heli theorem, it's a very precise one, saying that a pair of disjoint edges intersect. This is just using the fact that you cannot have an open set in RD which has D-dimensional homology or more. You think of that as some kind of non-embeddability theorem, but it's very weak. It's not saying anything about how things must intersect if this happens. So we're still using some sort of non-embeddability, and we're using it in this sense, that the nerve of an intersectional family of nice topological sets in RD is a D-Leray complex. Okay? And this gives you should think of this as giving you sort of restrictions on the complexity of the nerve complex. All right? And then what Kalai and Meshulam and others have done in the previous decade was show that all the fractional colorful Pq theorems are actually combinatorial consequences of this D-Leray condition. Right? So as soon as you have the D-Leray property, then these simplicial complexes satisfy all these things that these Heli theorems that I mentioned before tell you. So immediately you get the ones for convex sets, but you also get them for the nicely intersecting families. Sorry, the families of topologically nice subsets. Yeah? So that all comes from these D-Leray complexes. So this is a very powerful result. Now, what is the situation when the sets are less nice? So that's the thing I want to look at. And here's a theorem with two students, Mingi Kim and Sung Lee. So again, I'm back to the situation with intersectional family of open sets in the plane. And what we show is that for any such family, the nerve is 3-Leray. Right? Now, if they were not open connected, but they were like disks, topologically like disks, then the nerve theorem, the standard nerve theorem tells you that it's 2-Leray. So as soon as you allow holes in your sets, the Leray number will go up. You can make 2-dimensional homology in this situation, but you cannot make 3-dimensional or 4-dimensional. All right? So this is our main result, and as a consequence, we get all the Heli theorems that they asked for. We get the standard Heli theorem, we get the colorful Heli theorem with 4 families, and then if you do a little more work, you see that you get the fractional Heli theorem with Heli number 3, and you get the Pq theorem with lower bound 3 here. So P greater equal Q greater equal to 3. That does not follow directly from here. You need a little extra work, but that work is just combinatorial. You don't... As soon as you have this, then there's some additional combinatorial work, and you get these things. So that answers Xavier's question that indeed, for these not so nice sets, you get the same theorems, more or less. All right? And it comes from this fact. But this fact, well, it was not so... It took us some time to prove, and I asked many experts who know a lot about nerve theorems, and most of them told me that why would I even believe something like this could be true? But it turns out it was true. Okay, so let me explain simply basic outline of the proof. The basic outline is very easy. Here is one of the sets in my family. All right? So you fix this guy. Let me call him S0, the original family F0, the original nerve K0. Now fix one of the holes in the set. And since the family is finite, I can assume that there's a finite number of holes, and the holes are nice, and so on. Okay? And then fill in one of the holes. Okay? So the set grew a little bit. I changed the family to I replaced the original set with this new set here. And the nerve will grow a little bit, because there could be a bunch of things that intersect only inside this hole. The original set S did not intersect those guys, but when I fill in this, they will start intersecting. So the nerve, you need to add some simplices in your nerve. Right? And then you continue. And then you get this chain. The set is growing, the family is changing, and the nerve is growing. Yeah? And what you need to show is that along the way, the families are still intersectional. You need to show that if the three-dimensional homology, well, we show that if the three-dimensional homology at the ith step is non-zero, then it's still non-zero in the next step. Right? That's the key. And then you repeat this for every member in your family, and you show in the end that then you have an intersectional family of topologically nice sets. These are two-array. Then you're in the situation of the topological Heli theorem. This is a two-array family, so there's no three-dimensional homology, which means it must have been 0 at the beginning. Yes? So that's how you prove this. And step 1 and 3 are simple. Step 2 was where the problem was. I mean, this is an obvious approach, but the step 2 was the part that we needed some time to prove. And so let me explain a little bit about that with not too much details, because there's one thing in this proof that still is kind of a mystery to us, and maybe somebody can tell me later what they think this means. Okay, so the key to this step is given by a certain combinatorial identity that we found. So let me set this up. I take a simplicial 2 cycle, and I'm now working in Z2 coefficients. And I take the sum, so this is a collection of abstract triangles, so triples, okay? And then you order the triples. Take an arbitrary ordering of these triples, and then I'm going to define a 3 chain from this cycle. So for every I less than j less than k less than l, so for any ordered 4 tuple, I look at the intersection of I and k, so number 1 and 3, and the intersection of 2 and 4. Okay? And if this cardinality equals 4, then that is a 4 tuple, that's a 3 simplex, and I put this into my chain. Or that's a 3 simplex. That's essentially the join of 2 edges. All right? And then I define a chain called capital T, which is just the sum of all of these 4 simplices, and where the sum ranges over all these 4 tuples, ordered 4 tuples. Okay? I'll show you an example of this afterwards. So this is just a definition. So you start with a simplicial, with a 2 cycle and an ordering of the elements in that 2 cycle, and then you can get a 3 chain. And the identity is this one, that whatever 2 cycle you start with and whatever ordering you take, the boundary of that 3 chain is the original 2 cycle. Okay? And here is an example. This is a triangulated sphere with 5 vertices. Okay, so the 2 cycle are these triangles. Okay, and the ordering, in fact, it only matters if it's a cyclic ordering. So I'm ordering them starting, say, at 1, 2, 3, and I go around like this. That's my ordering. And what does this mean here? So, for example, the triangle 1, 2, 3 and the triangle 2, 3, 4, they have 2, 3, 5. They have 2 elements in common, 2 and 3. And here the triangle 1, 3, 4 and 1, 2, 4 have 2 elements in common, 1 and 4. And their intersection is this point. Sorry, that was a bad example. 1, 2, 2, 4, 5. Let me take this one. 2, 4, 5 and 2, 3, 5. They have 2 and 5 in common. And these 1, 2, 3 and 1, 3, 4 have 1 and 3 in common. And I include the join of those 2 pairs. That's this pink dot here. And that gives me the 3 simplex, 1, 2, 3, 5. And then when I sum over all of these, I get the following 3 simplices. Right? The 2 guys here, they cancel out because I'm working modulo 2. Okay?
So what are the edges in the right picture?
The edges in the right picture, I draw an edge when 2 triples have 2 elements in common. Yeah. So in fact, they correspond to edges here. Yeah, kind of. Yeah. Okay? And then if you change the ordering here, take a different ordering, this 3 chain is going to change. But the invariant here is that the boundary is always the same. Right? The boundary of that 3 chain always comes back to what you started with. And so that's, this is the identity which, of course, we can prove. Not too complicated. But we can also generalize it a little bit. I suspect that there is some general phenomenon. This is instance of a general identity, but I don't know what that is. I would like to know. Okay, now where does this come from? Let's go back to when I'm patching over that hole. Okay, so suppose that the second step in my proof was not working. So I had three-dimensional homology at the ith step, but the three-dimensional homology vanished in the next step when I filled this hole. Then, well, basically you can show that there is some set of 4 tuples, so a 3-chain beta of 4 tuples that intersect inside here, but do not intersect outside. Okay, so there's a bunch of 4 tuples who only intersect inside this hole that are creating the problem when you fill this in. Right? That's where the new simplices are going to be added. And you can show that the boundary of these are a bunch of triples, and they must intersect outside, which means they intersect the boundary of the hole. Okay? And the boundary of the hole is a cycle, and that gives you the ordering. Okay? Now suppose Ti and Tk, these are 2 triples that have 2 pairs, have a pair in common. By the connectedness assumption, it means that the pair that's inside Ti and Tk, they must intersect inside the set S. So there's a path here. And for example, Tj and Tl, they have something in common. So there's a path there. And by the order on the cycle here, that means that this simplex, so there's a pair that intersects here, a pair that intersects here, and they contribute into this cycle, this 3-chain that I called capital T. And so what this shows is that in the case if the homology vanishes in this step, then this 3-chain T is in the nerve. All right? But the boundary of that 3-chain is the original boundary here, and you can glue it to this beta, and you can use an induction and show that this kills the homology, which means that actually this cycle that supposedly vanished when you fill this in, it was already equal to 0. All right? So this is a way of killing. This combinatorial identity is something that kills homology. That's what we use it for. Okay? And so that's why we can prove this step, and that is the proof of this this Nerves theorem for connected sets. Okay, so I think I'll finish in time. You don't need to give a signal. I have a little bit more, but I'm almost done. So what are the further directions that we are working on? Of course, extend this to RD. That's a very natural program. So for example, my guess, I have an idea how to prove this now. If you have simply connected sets in R3, it's an intersectional family. This is a 4-Leray family. The nerve will be 4-Leray, right? Another direction that we looked into, which was interesting also, is instead of replacing R2 with a higher dimensional space, replace R2 by a graph. So R2 you can think of just as a grid, huge grid, right? And you have connected sets here. That's just connected subgraphs of this grid. Now why not replace that grid by another graph? And then it seems like it's related to structural graph theory. And so let me just give a quick definition. In the graph theoretic sense, my space instead of R2 will be a graph, and this intersectional family, that's a family of induced subgraphs such that the intersection of them is connected for any face in the nerve. Then using this concept, there's a natural way to define the dimension of a graph, and that is simply the maximum dimension for which there is a nerve, for which there is a connected family whose nerve has non-zero homology in that dimension D. And then you just maximize over all possible ways of covering this graph by a family. That's a natural dimension measure of the graph, or complexity measure of the graph, and it's not difficult to show that this parameter is a minor monotone parameter, meaning that if H is a minor of G, then the dimension of H is at most the dimension of G. And we can prove many things about this parameter, and another one of our results is the following, that if K3 is a minor in your graph, then the dimension is at least 1. If K4 is a minor graph, the dimension is at least 2. If K5 is a minor of the graph, the dimension is at least 3. And it leads us, of course, to conjecture this, that if KD plus 2 is a minor of G, if and only if the dimension is at least D. So this direction is easy. This direction is not so easy. The K5 case comes from this cycle that I showed you. Yeah. Okay, so I think that's it. Thank you.